All right, we're looking at section 7.4 on logarithms. So we're looking at how do we use logarithms. And logarithms are used to solve equations where the variable is in the exponent. So previously we would not be able to solve this problem because we don't know what to raise 2 to get 6. Okay, because it's not a nice even number. Okay, so the general definition of a logarithm is in this box, and we need to know that. So if b to the x equals y, then x equals log base b of y is how you'd read that. Okay, and the first part of this section just focuses on can you rewrite equations in each form, in equivalent forms. So this first one, if I want to rewrite this from a logarithm to an exponent, because these are equivalent, then I would look, and the base stays the same in both. X is my exponent, so this would be 2 to the 4 equals 16. That's how I'd write that one. And if I wanted to go from exponential to logarithm, I would set everything equal to the exponent, which is 3 in this case, equals log base 3 of 64. Or base 4, I'm sorry. Base 4. 4 is my base. Okay? We'll also be able to evaluate these logarithms. Okay? So you're simply trying to figure out what this equals. And if I rewrite this as an exponential, I'd be asking myself 2 to what power equals 8? Well, we know that 2 to the third equals 8, so this answer is 3. Okay, if I set it equal to x, we can just rewrite it as 3 to the x equals 81. So what do I have to raise 3 to get 81? And that would happen to be 4. Okay, how about this one? 27 to what power gives me 3? This one might be a little more difficult. So we need to think about a fraction on this one. It's actually 1/3 because the cube root of 27 is 3. Okay, this one 1/2 to what power gives me 8? Okay, I know 2 to the third is 8, so 1/2 to the negative 3 equals 8 because I have to flip that. The negative allows me to flip that fraction and make it positive. So 1/2 to the negative 3 is the same as 2 to the third, which is 8. So that's how we use the definition of a logarithm to evaluate those logarithms. Okay, further in this section, we talk about inverse functions. So if g of x equals log base b of x, then b to the g of x equals x. That's based on this definition here. The base to this power equals x. Okay, so if I swap these to find the inverse, remember when we find inverses, we just swap the variables. And this is my variables. This is my variable here. Then this is my inverse, and I just rewrote it as g inverse would equal b to the x. Okay. So you can see an exponential is the inverse of a logarithm. Okay, so let's just say f of x equals b of x, so we have different variables here, and g of x equals log base b of x. That means these are inverses of each other. And if I take the composition of an inverse, if you remember back to chapter 6, the composition of an inverse when we plug them into each other simplifies down to x.
Please excuse this announcement.
So,
there is construction that's going to happen.
so if I substitute the f of x equation into the g equation, it's going to look like this. And that's going to equal x. Same thing here. If I plug the log equation into the exponent, it'll simplify to x because they're inverses. Okay. Now, why do we need these? It's just simply to simplify expressions. So the key thing to notice is the bases are the same in both. Okay. So if I have an expression like this on the bottom, and I notice the bases are the same, this simplifies just to x. Okay, whatever this is.